So this is a quick solution of the sub-exercise put in this exercise 37. So there we say that direct experiment, what we need is that showing that in category of finite happening groups, we want to show that there are not enough injectives. Actually, the claim is that there are no non-zero injectives. There are no non-zero injectives. Any injective module in the category of finite happening groups should be 0. So to prove it, that we give proof that any z quotient by p power would not be injective. And I left that sub-exercise to show that this already show that no non-zero finite happening groups could be injective. The argument is that any direct experiment of injective is again injective. So in that case, it suffices to show that for finite happening groups, it suffices to show that the quotient by p to the power I is not injective, and then a direct sum of those p quotient, the quotient by some prime power, would not be injective. Okay, so it's sufficient to show this. To show this, we could prove something more general. Let's say you got your injective I, for example. What do we mean that you have a direct experiment? Maybe it's better to call it injective map. Here we have this inclusion, right? So more abstract, more general would be that you have a retract of I is injective module in some category C, and then there exists section or retraction such that this composition is identity, and so this is surjective map. The argument is that you want to show that in the category of C, if you have any monomorphism from A to A prime and any map from A to J, then we claim that there is a unique factorization. The argument is that through this embedding to injective I, there exists a unique, let's say f factorized. There exists a unique f such that the diagram commutes, and we claim that this factorized. The reason it factorized is that, notice that, I call this f prime defined to be f, defined to be s composed with f, works because, so you have some A prime, you map it to f of A prime, and then here you have this s f A prime. Okay, this is our definition of f prime. The question is, in that diagram commutes, which means prime maps to sf A prime, then map to I s f A prime, but this I s is identity, so this is f A prime, so indeed it commutes with, okay, make diagram commutes. So is this unique? Suppose you have two different ones. Notice that this I composite are the same because the diagram commutes both equals f. Right, and then this i's monomorphism would imply that you could cancel from left, and this must be the same. Okay, why I is monomorphism. So in this case, this is clear. This is monomorphism. So in general, what you have is you have this is identity, and so I compose with f prime equals I compose with f double prime. You apply this s, this would tell you that f prime equals f double prime, so it's monomorphism actually. Okay, actually we don't need this monomorphism. Actually this shows f is monomorphism, and so this finishes the proof. There exists a unique factorization. The diagram commutes.